The afternoon link first topic is efficiency of a Carnot engine. Efficiency is defined as the ratio of work done by the working substance in one cycle to amount of heat extracted from the source. That means eta is equal to work done by heat extracted is equal to W by QH. From the first law of thermodynamics, W is equal to QH minus QL. That is, theta is equal to QH minus QL by QH is equal to 1 minus QL by QH. Applying thermal conditions, we get QL is equal to mu R TL logarithmic V3 by V4. So here we omit the negative sign since we are interested in only the amount of heat ejected into the sink. We have derivative QL by QH is equal to TL logarithmic V3 by V4 and TH logarithmic V2 by V1. By applying adiabatic conditions, we get TH V2 gamma minus 1 is equal to TL V3 gamma minus 1. Like that, by dividing the above two equations, we get V2 by V1 gamma minus 1 is equal to V3 by V4 gamma minus 1. So, which implies that V2 by V1 is equal to V3 by V4. Substituting equation 8.65 in equation 8.64, we get QL by QH is equal to TL by TH. The efficiency eta equal to 1 minus TL by TH. The important results: eta is always less than 1 because TL is less than TH. This implies that efficiency cannot be 100%. It can be 1 or 100% only when TL is equal to 0 Kelvin. That means absolute zero temperature, which is impossible to attain practically. 2. Efficiency of the Carnot engines is independent of the working substance. It depends only on the temperature of the source and the sink. The greater the difference between the two temperatures, higher the efficiency. When TH is equal to TL, the efficiency eta is equal to 0. No engine can work having source and sink at the same temperature. The entire process is reversible in the Carnot engine cycle. So, Carnot engine is itself a reversible engine and has maximum efficiency. But all practical heat engine like diesel engine, petrol engine and steam engine have cycles which are not perfectly reversible. So, their efficiency is always less than the Carnot efficiency. This can be stated in the form of the Carnot theorem. It is stated as follows: between two constant temperatures reservoirs, the only Carnot engine can have maximum efficiency. All real heat engines will have efficiency less than the Carnot engine. Our next topic is entropy and the second law of thermodynamics. We have seen in the equation 8.66 that the quantity QH by TL is equal to QL by TL. The quantity Q by T is called entropy. It is a very important thermodynamic property of a system. It is also a stable. It is also state variable. QH by TH is the entropy received by the Carnot engine from hot reservoir, and QL by TL is the entropy given out by the Carnot engine to the cold reservoir. For reversible engine, Carnot engine, both entropies should be same so that the change in entropy of the Carnot engine in one cycle is 0. This is proved in equation 8.66. But for all practical engines like diesel and petrol engines, which are not reversible engines, they satisfy the relation QL by TL greater than QH by TH. In fact, we can reformulate the second law of thermodynamics as follows: for all the process that occur in the nature, that means irreversible process, the entropy always increases. For reversible process, entropy will not change. Entropy determines the direction in which natural process should occur. We know. Come back to the question: why does heat always flows from a state of higher temperature to one of the lower temperature and not in opposite direction? Because the entropy increases when heat flows from hot object to the cold object. If heat were to flow from cold to a hot object, entropy will decreases, leading to violation of second law of thermodynamics. Entropy is also called a measure of disorder. All natural processes occur such that the disorder should always increases. Consider a bottle with a gas inside. When the gas molecules are inside, the bottle has less disorder. Once it is spread into the entire room, it leads to more disorder. In other words, when the gas is inside the bottle, entropy is less than the once the gas spreads into entire room, the entropy increases. From second law of thermodynamics, the entropy always increases. If the air molecules go back into the bottle, the entropy should decrease, which is not allowed to by the second law of thermodynamics. The same explanation applies to a drop of ink diffusing into water. Once drop of ink spreads, its entropy is increased. The diffused ink can never become a drop again, so natural process occurs in such a way that entropy should increase for all irreversible process. Next topic is refrigerator. A refrigerator is a Carnot engine working in the reverse order, which is given working principle. See that this is the diagram for refrigerator, hot reservoir and cold reservoir. Here the temperature flows from cold reservoir to hot reservoir. Now we will see the concepts. The working substance gas absorbs a quantity of heat QL from the cold body sink at a lower temperature TL. A certain amount of work is done on the working substance by the compressor and a quantity of heat QH is rejected to the hot body. That means the atmosphere at TH. When you stand beneath of refrigerator, you can feel warmth air. From the first law of thermodynamics, we have QL plus W is equal to QH. As a result, the cold reservoir refrigerator further cools down and the surroundings, kitchen or atmosphere gets hotter. Coefficient of performance, that is beta. COP is measure of the efficiency of a refrigerator if it defined as ratio of heat extracted from the cold body sink to the external work done by the compressor W. COP beta is equal to QL by W. From the derivative 8.68, beta is equal to QL by QH minus QL. Beta equal to 1 by QH by QL minus 1. So, but we know that QH by QL is equal to TH by TL. Substituting this equation into equation 8.70, we get beta is equal to 1 by TH by TL minus 1 is equal to TL by TH minus TL. Inferences. The greater the COP, the better is the condition of refrigerator. A typical refrigerator has COP around 5 to 6. Lesser the difference in the temperatures of the cooling chamber and the atmosphere, higher is the COP of the refrigerator. In the refrigerator, the heat is taken from cold object to the hot object by doing external work. Without external work, heat cannot flow from cold object to the hot object. It is not violation of second law of thermodynamics because the heat is ejected to surrounding air and the total entropy of refrigerator plus surrounding is always increased. Our next lesson is oscillations. We skip lesson number 9 that we will see during the class hours. We will see now oscillations. So, introduction. What is have you seen that Tanjavur dancing doll? In Tamil it is called Tanjavur Dalayatti Bommai. It is a world famous Indian cultural doll. What does this doll do when disturbed? It will dance such that head and body move continuously in a to and fro motion until the movement of gradually stops. Similarly, when we walk on the road, our hands and legs will move front and back. Again, similarly, when a mother swings a cradle to make her child to be asleep, the cradle is made to move into and fro motion. All these motions are different from the motion that we have discussed so far. These motions are called oscillation, oscillatory motion or vibratory motion. Similar motions occurs even at atomic level. When the temperature is raised, the atoms in the solid vibrate about their mean position or equilibrium position. The study of vibrational motion is very important in engineering applications, such as designing the structure of building, mechanical equipments, and etc. First topic is periodic and non-periodic motion. Motion in physics can be classified as periodic motion and non-periodic motion. What is meant by periodic motion? Any motion which repeats itself in a fixed time interval is known as periodic motion. Example, hands in pendulum clock, swings of a cradle, the revolution of earth around the sun, waxing and waning of motion, etc. Non-periodic motion. Any motion which does not repeat itself after regular intervals of time known as non-periodic motion. Example, occurrence of earthquake or eruption of volcanoes and etc. Oscillatory motion. When an object or a particle moves back and forth repeatedly for some duration of time, its motion is said to be oscillatory or vibratory motion. Example, our heartbeat, swinging motions of the wings of an insect, grandfather's clock, that means pendulum clock, and etc. Note that all the oscillatory motions are periodic, whereas all the periodic motions need not be oscillation in nature. Simple harmonic motion, SHM, equilibrium position. A simple harmonic motion is a typical type of oscillatory motion, but all oscillatory motions need not be a simple harmonic motion. Simple harmonic motion is a special type of oscillatory motion in which the acceleration or force on the particle is directly proportional to its displacement from a fixed point and is always directed towards the fixed point. In one-dimensional case, let x be the displacement of the particle and ax be the acceleration of the particle, then ax directly proportional to x and ax is equal to minus bx. Here b is a constant which measures acceleration per unit displacement and dimensionally it is equal to t minus 2. By multiplying mass of the particle on both sides equation from Newton's second law, the force is Fx is equal to minus kx, where k is a force constant which is defined as force per unit length. The negative sign indicates that displacement and the force or acceleration are in opposite direction. This means that when the displacement of the particle is taken towards right of equilibrium position, the force will point towards equilibrium towards left, and similarly when the displacement of the particle is taken towards left of the equilibrium position, x takes negative value, therefore the force or acceleration will point towards equilibrium towards right. This type of force is known as restoring force because it's always direct the particle executing simple harmonic motion to restore its original equilibrium or mean position. This force, restoring force, is central and attractive, whose center of attraction is the equilibrium position. In order to represent in 2 or 3 dimensions, we can write using vector notation. That is, F vector is equal to minus kr vector, where r vector is the displacement of the particle from the chosen origin. Note that the force and displacement have linear relationship. This means that the exponent of force F vector and the exponent of the displacement r vector are unity. The sketch between the Gauss magnitude of force F vector and the effect magnitude of displacement r vector is a straight line passing through the second and fourth quadrant shown in the diagram. you can see that clearly. A body moves in a circle which is executing simple harmonic motion. By measuring slope 1 by k, one can find the numerical value of the force constant k. Now, projection of uniform circular motion on a diameter of SHM. Consider a particle mass m moving with uniform speed v along the circumference of the circle whose radius is r in anticlockwise direction. Let us assume that origin of the coordinate system coincide with the center of O of the circle. If omega is the angular velocity of the particle and theta is the angular displacement of the particle at any instant of time t, then theta is equal to omega t. By projecting the uniform circular motion on its diameter gives a simple harmonic motion. This means that we can associate a map or a relationship between the uniform circular motion or revolution motion to vibratory motion. Conversely, any vibratory motions or revolution can be mapped to uniform circular motion. In other words, these two motions are similar in nature. So this is the diagram for a particle moves in a circular which is executing simple harmonic motion. Let us first project the position of a particle moving on a circle onto its vertical diameter or onto a line parallel to the vertical diameter. Similarly, we can do it for horizontal axis or a line parallel to the horizontal axis. This is the each and every steps of a body moves in a circular orbit exhibiting simple harmonic motion, that means linear motion. As a specific example, consider a spring mass system. When the spring moves up and down, the motion of the mass or bob is mapped to points on a circular motion. Thus, if a particle undergoes uniform circular motion, then the projection of particle on the diameter of the circle traces straight line motion which is simple harmonic in nature. The circle is known as reference circle of the simple harmonic motion. A simple harmonic motion can also be defined as motion of the projection of a particle on any diameter of a circle of reference. Displacement, velocity, acceleration and its graphical representation, SHM. So, displacement, velocity and acceleration executed by a particle moving in a circular path exhibiting simple harmonic motions. See the diagrams. The distance travelled by the vibrating particle at any instant of time t from its mean position is known as displacement. Let p be the position of the particle on a circle of radius a at some instant of time t. Then its displacement y at that instant of time t can be derived as follows in OPN. Sin theta is equal to ON by OP is equal to ON is equal to OP sin theta, but theta is equal to omega t on y. ON is equal to y and OP is equal to a. Y is equal to a sin omega t. The displacement y takes maximum value which is equal to a. The sin omega t is equal to 1. This maximum displacement from the mean position is known as amplitude of the vibrating particle. For simple harmonic motion, the amplitude is constant, but in general, for any motion other than simple harmonic, the amplitude need not be constant. It may vary with the time. Velocity. The rate of change of displacement is velocity. Taking derivative of equation 10.6 with respect to time, we get v is equal to d by dt is equal to d of a sin omega t by dt. For circular motion, constant radius, the amplitude a is constant, and further for uniform circular motion, angular velocity omega is constant. Therefore, v is equal to d by dt is equal to a omega cos omega t. Using trigonometry identity, sin square omega t plus cos square omega t is equal to 1. Cos omega t is equal to root of 1 minus sin square omega t. So, v is equal to a omega root of 1 minus sin square omega t. From the derivative 10.6 sin omega t is equal to y by a, v is equal to a omega root of 1 minus y square by a square. That means v is equal to omega root of a square minus y square. When the displacement y is equal to 0, the velocity will be a a omega, and for the maximum displacement y is equal to a, the velocity v is equal to 0. As the displacement increases from 0 to maximum, the velocity decreases from maximum to 0. This repeated, since the velocity is a vector quantity, derivative 10.7 can be also reduced by resolving into components. So we'll see next class. Thank you children. Go through the topics what is taken from the lessons. Thank you.